Anyway, as I was telling you, I selected the subject because it's something that this noise is annoying. So, can we filter all the noise? So, let's talk about Gnss for climate. And I'll try to explain to you the importance of Gnss data. It's actually, you have seen Gnss a little bit, and we're going to talk about a specific application. Okay, and the application comes from the fact that the Gnss data is of really high quality. So the first thing that I like to stress is what is a great American physicist and Nobel Prize in Physics laureate Richard Feynman said once. He stressed the importance of matching the theory with observations. So he said, it doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with the experiment, it is wrong. So it doesn't matter how beautiful you have a model, it has to fit with it has to be validated by the observations. And I'm saying that to stress the fact that if by any chance we have a very good model, but if our data is not reliable, our estimates are going to be bad. Alternatively, if we have very good data, but the model is not realistic, we're going to have bad estimates. So we need to have good data, good model, in such a way that we have good estimates. Now, where our good data is going to come, in our context here, we're talking about specifically delay that the electromagnetic signals coming from Gnss suffer when crossing the lower layer of the atmosphere. So let's just make a brief overview about ionospheric and tropospheric delays that I believe Michael discussed a bit. And if we have this scenario here, we have this is the satellite, Gnss satellite, and this is a receiver. The lowest layer that we have is where we live, okay, where all the meteorological phenomena takes place. Okay, so that's where we have where feel cold, feel hot, and it's wet, it's dry, and there is pressure, low pressure, high pressure that will bring the weather fronts. We call that the troposphere. And for us, the most important parameters that represent the troposphere are pressure, temperature, and relative humidity. There is another layer, the one up there, and this is a simplified diagram, of course. One that the phenomena that happens there is that we have these atoms, and there is radiation that comes from the sun, and some of the electrons get so excited that they go free. Okay, they're called the free electrons. We call this layer the ionosphere. And the interest for us is the TEC, the total electron content, so the total number of free electrons. And what happens that the signal from GPS to receiver, it doesn't go through a straight line, it gets refracted, and gets refracted when it crosses the ionosphere as a function of the TEC, and gets refracted when it crosses the troposphere, and that's going to be a function of pressure, temperature, and relative humidity, water vapor. So there was something I forgot to do here. I'm going to just start here. So for us, is the troposphere is the most important layer, and for our objective. Oops, it came all the way again. Okay, now let's look how we can do meteorology with that. So again, let's consider that we have these observation propagating from satellite to receiver, and we want to determine the delay. The delay and delay is essentially something I forgot to mention to you. The delay would be the difference between the actual path that is in red and the theoretical path that is in black. So the difference between them we call the delay, because basically the signal would arrive later, delayed, instead of if it were comparing to coming on a straight line. So we want to get the delay point in the zenith, that is the higher point, but we actually measure the delay along the path. We call that the slant delay, and that's a function of this elevation angle E. So we have the so-called STD, that's the slant total delay, and we can establish a ratio with the zenith total delay. It's roughly the inverse of the sine of the elevation angle. We call that a mapping function. So this is very important, and I'm going to focus on the ZTD. Okay, so we go beyond these relations is important. This one for us is going to be the fundamental one. The total delay is composed of two components. We have the zenith hydrostatic delay, ZHD, and we have the zenith wet delay, okay, ZWD. The hydrostatic can be represented as a function of pressure, the wet as a function of relative humidity or water vapor. So ZTD and ZWD are computed by Gnss. Okay, ZHD, which is a function of pressure, is usually modeled. It's easier to model. And the interesting thing is that the zenith wet delay, which contains the moisture, we can use that to compute the so-called PWV, which is precipitable water vapor. So basically, we can check the water vapor along the column, and that's something very important for us, for weather, also for climate, because water vapor is the most important greenhouse gas. CO2 is trace as compared to water vapor. So ZTD has been used by some meteorological offices already. For example, the UK Met Office. I like to quote this gentleman, Owen Lewis, who kind of 2 years ago already, he's mentioned that GNSS was the second best parameter provider of ZTD for the UK Met Service. And the important thing that ZTD and ZWD, they are unaffected by ground influences. Okay, so satellite data in general can be used as independent constraints for models. Can fit the models, can also be used as constraints to models. So satellite data here will be a general term, including GNSS, but I'm also referring to the satellite data that we can measure indirectly the temperature from satellite, but I'm not talking here about my discussion on GNSS. And we can also do so-called radio occultation with GNSS, which I'm also not talking about that. I'm talking about here observation, satellite GNSS observation collected by ground receivers. Now, look at these here independent constraint to models, unaffected by ground influences. Let me just give an example of what ground influence may be. So let's have a look at one effect that impact meteorological stations around the world due to the so-called urban island effect. So let's have this case station in Argentina, these two, and they're south of Brazil, so I chose them because they're down there. And we have this station in Buenos Aires Observatory, which has records since 1880. And there is a station in Uruguay called Mercedes, which has records since 1909. Okay, it's most long-term records are either in Europe or U.S. It's difficult to find long records close together like that. So the important thing is that these stations are located in two different places. So on your left we have Buenos Aires, and this station, meteorological station, is right in the middle of the city. Okay, and on the other hand, the Mercedes is right where it should be, in the rural area. Okay, far away from a city. So what happens then is that the station of Buenos Aires is affected by this urban island. If you look at these two plots, and I'm going to explain to you, they show the mean temperature, okay, annual mean temperature from the left. Your left is Buenos Aires, from the right is Mercedes. Let's look at Buenos Aires first. The yellow is the actual data, okay, the actual data. So we can Buenos Aires. So we can see that it was kind of flat from 1880 to 1920, and then it started to grow. And most likely the growth is actually because the city was growing, and the meteorological station was in the urban area, then became surrounded by concrete. Here we can see in yellow the raw observation from Mercedes, and we can see that it's basically flat. In black is the so-called homogenized data. It's a big adjustment where in this case is it's basically NASA, the GISS office. They put together these temperatures, and they try to accommodate one on the other with the other. So what happens here, we can see that the urban island effect in Buenos Aires is actually got absorbed. The actual adjusted or homogenized trend started now with 17 degrees, 1 degree above, but contains the effect of the urban island. And Mercedes now shows also a slight increase due to the same thing. So what happened is that again, satellite data will be not affected by this type of phenomenon. Now, this is just for curiosity to stress that nonetheless, okay, when you put together satellite and ground temperature, in this case, that's what we represent here with in green, okay, the reanalysis. And this shows a time series from 75 until 2018. And we have also measurements from satellite. So what we see here is basically, these are the observations, and all these macaroni plot that you see is basically all the models, climate models, and some of them go far away, some follow very well the data. The best ones actually the Russians. The Canadians are the ones that say that there's warming more. I think that's wishful thinking, right? But anyway, this is why we need good data. We need reliable data, okay, so that we can assert models. And that data, the models also have to include all sorts of parameters. So this is a plot just out of curiosity that shows compare the hydrocarbon in here. So going from 1880 to 2000. In blue we have temperature. This is the Arctic temperature, and in red we see the this solar irradiance. So I mean, pointed out the importance, of course, of the amount of solar irradiance on temperature. So these emphasize. So we have seen that GNSS will provide can provide water vapor information, okay, and the importance of good, reliable data in such a way that we can build better models, validate models, etc. What happens is that when we look in terms of climate, there are some criteria that has to be established, and one of them is that, as defined by the World Meteorological Organization, they prescribe the use of so-called climate normals. Climate normals, we can think of that as a mean over 30 years. Okay, so basically we need 30 years of data to start to have a parameter that we can use for climate. We can also try to look at trends. This is something else that is important. Okay, so what is plot here, it just shows the importance of these 30 years. Okay, we have here the computation of normals or mean values for periods of 10 years all the way to 30 years. So in red we have the 30 years normals. Okay, and you can see that there is much more variation when we take the means over a shorter period of times than when we take means over a longer period of times, which is something logical. So, so there is some wisdom in the use in thinking, in trying to think in terms of climate with long terms, with normals every 30 years. So, okay, where my research fits on that? We have been working in terms of quality control of series of zenith total delay, zenith wet delay. There are also gradients, which I haven't really discussed with you here. Looking at climate. The whole thing is GNSS. GNSS, well, first GPS started with continuous observations on a regular basis in 1994. So, which means we are 4 years away from the 30 years, okay? Which means that GNSS will be qualified, let me say it like that, to provide climate normals, okay? And we have to make sure that the value that we provide, these climate normals, will be derived from time series of ZTD or ZWD. They're the best that we can provide. And there is also the issues of trend. Okay, so I'm showing you here a pilot project that we did. We got these stations in Europe. They have been processed over a period of 13 years and generating the ZTDs and ZWDs, and by different centers. So we have different solutions, okay? And then we start to look how these differences compare in such a way to see how much we still need to go in terms of quality control. So I'm going to show here the trends because of the time that I have. And let me explain what this is, okay? Here we have, on the horizontal axis, we have all these stations. Mate is one of the stations, okay? In Italy, Matera, we have Medi, there, Metz, another station. So we have each tick here represents a station. And we have groups of rectangles that represent different solutions coming from different organizations, okay? And they use different software, they use different algorithms. The data set is the same. And then what we have here is a trend. For example, for Matera, we have all solutions showing a positive trend of about 0.1 millimeter per year. That's how much variation in ZTD. ZTD means pressure, temperature, and relative humidity. Okay, so that's a small variation, but that's what we're looking at. And but then there is a yellow there that points negative. Okay, and why is that? So we can see the station MEDI that has positives and negatives, and so all the other ones, okay, groups of colors, they represent then different solutions indicating different trends. Okay, and the whole thing that we have in mind now in this particular research is actually to establish quality control mechanisms that we can really define how reliable the data is and how reliable the information that we're going to offer to the to climate, which means the parameters and also their trends, or trend of the parameters, can be of good quality. Okay, so my concluding remarks in here is that we need reliable data sets and realistic models. GNSS data sets have been continuously collected since 1994, which means that we're very close to have these 30-year period that we can actually estimate normals. GNSS contribution to numerical weather models is a growing reality, which means that these models that are used for weather forecast, lots of them already incorporate GNSS information. GNSS contribution to climate models is growing importance as the time series of GNSS becomes long every day. So every day that passes, the time series gets longer and longer and longer, and hopefully forever. Just so that you understand where this work fits in, I'm co-chairing a working group with Dr. Rosa Paccioni from Italy that deals with this topic. It's called Quality Control Methods for Climate Applications of Geodetic Tropospheric Parameters, under the auspices of the International Association of Geodesy. Okay, so I think I will stop here within my 20 minutes, 25.